Hello and welcome back to Functional Analysis. First, big thanks to all the nice people who support my channel on Steady or PayPal. Now, this is part 2 of the series, and today we go deeper into the topic of metric spaces. We've already learned if we have a set X and a metric for this set, then we call this a metric space. In a metric space, one can now generalize a lot of notions you may know from a real analysis course. For example, we can define sequences, limits, accumulation points, and so on. Of course, this is what we will use a lot in this series. However, before we do that, let's talk about some examples. So let's start with a simple one, which is also one of the most important ones. The set is just the complex numbers, and the metric should be the usual notion of measuring distances in the complex numbers, which means it's the absolute value where we look at the difference of both points. Now, the visualization in the complex plane gives us indeed the normal geometry we have in the plane. If we pick two complex numbers x and y, we know we can calculate the difference, which is a new complex number. And the length of this new complex number is exactly the distance we want. Now you know this normal geometry we have for measuring distances you can also do in higher dimensions. For example, if the set is Rn, we would have a standard metric we can choose, and this is usually called the Euclidean metric or the Euclidean distance. And because you know Pythagoras' theorem, you also know the definition of d. It's just the first component of x minus the first component of y squared plus the second component, and so on until you reach the last component, which is xn minus yn squared. And then, of course, we need the square root. Okay, so this is the Euclidean metric, the common but only a possible choice of a metric in Rn. So please remember, for a metric we only need the three properties. It should be positive definite, symmetric, and fulfill the triangle inequality. We already know that these two fulfill the three properties, so they are metrics on Rn or C respectively. So let's look at another distance function we could define for Rn. This would be the maximum, and then we look at the difference x1 minus y1 and use the normal absolute value or modulus in R. So let's write it down for all components, which means we want the maximum of all these differences. In fact, this is of course a metric as well. It's not hard to check that it fulfills our three properties, and most of the time only the triangle inequality needs some work. However, we should first visualize the whole thing, maybe again in the plane. So here we see 2 points, x and y, and what we now have to do is calculate the distances of the components here. Now in blue we have the distance in the first component and in green in the second component. And as you can see, the blue one is bigger, so the maximum is indeed this number here. Which means using this metric, this is exactly the distance between x and y. Or in other words, if you choose a point z here, for example, it has the same distance from x than the distance x to y. Of course, this shouldn't be so surprising. Of course, you could have different points that have the same distance from a chosen point x. In our Euclidean metric from above, or in a picture in a complex plane, this would be just a circle around x. However, with another metric, such a thing we could call a circle might look completely different. Okay, so please keep that in mind whenever we use circles to visualize things. For our last example here, let's choose a more abstract one, just any set x, which should not be the empty set. Then we define a metric by distinguishing two cases. The first case is just x is equal to y, and the second, of course, x is not equal to y. By the first property of the metric, we already know here we need a 0. However, we are not allowed to have a 0 here, so we can choose whatever we want, and most of the time we just choose 1. Okay, so let's check together that this is indeed a metric. As it happens very often, the first two properties are not a problem at all. It's positive definite by our construction, so no problem here. The second property is the symmetry, and here you can see the whole definition is symmetric, so no problem here at all. The third property is the triangle inequality, and this one I want to write down. In order to show that, we need 3 points, so x, y, and z out of the set, and then we look at the inequality. This means that we go the detour over the point z, or in other words, we add the distances on the right. Okay, so this is what we have to show in general. So let's first look at 2 different cases. Now the first case would be x is equal to y, and because then we know the distance of x to y is exactly 0. Okay, so let's write that here. This is 0. Okay, but then we know this inequality is correct because on the right hand side we just have the metric or the distances, and we already know they are positive or 0 in the worst case. This means that the triangle inequality in this first case is satisfied. Now the second case of course should be the opposite, so we have x is not equal to y, which means the distance is by definition exactly 1. Now because we know that the only allowed distances are 0 or 1, there's nothing in between, we know that xz or zy have also 1 or 0. Or to put it in another way, we know that dxz or the other one, so zy, is also exactly 1. At least one of them has to be 1. Otherwise both of them would be 0, which means that z is equal to x and z is equal to y, but then this would be not the second case. However, this means now if we add both of these distances, we will get 1, or in the worst case when both of them are 1, we get out 2. So we have the inequality. So very good. Also in the second case, the triangle inequality is fulfilled. Well, now to close this example, let's recall that this definition defines a metric, it works on any set, and it's called the discrete metric. So you might try to visualize this metric space. It's a little bit strange because there are no neighbors around a given point, simply because there's a fixed distance from one point to all the other ones. This means that all the points are isolated points. Okay, so now we have a few examples of metric spaces we can work with, and in the next video I will talk about other objects we find in metric spaces. So, thanks for listening, and I hope I see you in the next video. Bye!